I want you to imagine, just for a second, that you're the captain of a massive commercial cargo ship.
Oh, man. High-stress job.
Right. You're standing on the bridge, you're looking out over thousands of shipping containers, and you're tasked with navigating not just the unpredictable physical oceans, but this invisible, overwhelmingly complex web of international environmental laws.
Yeah, and that web is constantly changing.
Exactly. The most difficult part of your job isn't a hurricane. It's the fact that this web of laws completely changes depending on exactly where your ship is sitting in the water at any given moment.
It's basically a shifting geographic puzzle.
Yeah.
And what we see happening today is a situation where the rules of physics, the realities of marine engineering, and the dictates of international maritime law are just violently colliding. I mean, on a daily basis.
And that collision is exactly what we're exploring in this deep dive. We're looking at a genuinely eye-opening article from a publication called The Deep Draft.
Yeah, it's a great piece.
It really is. It's titled EGCS, MARPOL Annex 6, and the Reality at Sea. And, what makes this material so compelling to me is the author. It's written by a serving master mariner, Captain Raghu Sharma.
Which is huge. He's actually out there on the water right now dealing with this exact regulatory nightmare.
Exactly. Getting that perspective is rare, right? We so often consume information about global environmental policy from the policymakers, the people drafting documents in, landlocked boardrooms in Geneva.
Right, the people who never actually have to turn a wrench. Captain Sharma is giving us the view from the bridge. And honestly, perhaps more importantly, the view from deep down inside the ship's engine room.
Yeah, the sweaty mechanical reality of it all. So whether you're interested in global supply chains, environmental policy, or you just love learning how massively complex machinery actually works, you're going to see how supposedly simple environmental solutions almost always trigger a cascade of just wildly dangerous complications.
Because when you attempt to regulate an industry as sprawling and, well, foundational as global shipping, a minor oversight in policy design on land can instantly become a colossal mechanical crisis out on the water.
Right. So to understand how that happens, let's lay the groundwork. Let's talk about the rule that started it all.
Good place to start.
Captain Sharma walks us through a global regulation known as MARPOL Annex 6X. At its core, this is a rule that mandates a strict limit on sulfur oxide emissions for ships operating outside of designated emission control areas.
Yeah, the global limit is capped at 0.50% mass by mass.
Right. And sulfur oxide, or SOx, is heavily regulated for a very good reason, right?
Oh, absolutely. It's a major atmospheric pollutant. It's a primary driver of acid rain. And it has severe, really severe impacts on human respiratory health, especially in coastal communities. So capping that sulfur content in marine fuels globally is a monumental effort to clean up the air we all breathe.
The intent is incredibly noble. Nobody's arguing that. But obviously, commercial cargo ships run on fuel. Historically, they've run on a very specific type of fuel called high sulfur fuel oil, HSFO.
Yeah, but the dirty stuff.
Right. From what I understand, this stuff is cheap. It packs massive amount of energy, but it is, as the name makes very clear, loaded with sulfur.
Right.
So the global shipping industry is suddenly handed this mandate to drastically cut these emissions. And they didn't just stop sailing. So how did they adapt?
Well, the article details how the industry started installing these massive retrofits called exhaust gas cleaning systems. You'll hear them referred to informally across the industry as scrubbers.
Scrubbers? Okay, so I've always pictured this as like a giant multi-million-dollar Brita filter bolted onto a factory smokestack.
A Brita filter, that's a funny visual.
I mean, right. The ship keeps burning the cheap, dirty fuel, but this massive filter catches all the bad stuff before it hits the atmosphere, so the ship technically isn't violating the rules.
I see why you'd use that analogy, but actually misses the fascinating chemistry of how these systems work.
Oh, really?
Yeah, because a Brita filter physically traps particles inside a porous material, like carbon. A marine scrubber is entirely different. It's essentially a massive chemical shower system installed inside the ship's exhaust funnel.
Wait, a shower system inside an exhaust pipe?
Precisely. It's wild. Yeah. As the highly toxic sulfur-rich exhaust gas rises up the funnel, the scrubber system sprays massive volumes of water, usually raw seawater, downward into the gas.
Okay, so it's washing the smoke.
Basically, yeah. See, seawater is naturally alkaline. When that alkaline water meets the acidic sulfur dioxide gas, a chemical reaction occurs. The water literally washes the sulfur out of the exhaust, neutralizing it and turning it into harmless sulfates dissolved in the water.
Wow.
Then the clean air continues up and out the funnel, and the wash water is collected.
That is wild. It's literally a localized rainstorm inside the smokestack creating a chemical reaction.
Yep.
So the ship gets to keep burning the cheap, energy-dense, high-sulfur fuel oil, but the air coming out the top meets that 0.50% global standard.
Exactly. It's a very clever engineering workaround.
But honestly, building a multi-million-dollar chemical processing plant inside a smokestack feels like a massive technological workaround to a fundamental chemical problem. Like, why not just force everyone to burn clean fuel in the first place? Why go through the trouble of scrubbing dirty fuel?
And that question cuts to the absolute heart of the systemic flaw Captain Sharma identifies in the article. You have to look at who is actually making the rules.
Okay.
The International Maritime Organization, or the IMO, is the UN agency responsible for regulating shipping. But, and this is the key, the IMO's jurisdiction strictly ends at the ship's hull.
Meaning they only have authority over the ships themselves.
Exactly. They cannot dictate terms to the massive multinational oil majors or the onshore fuel terminal.
I see.
Yeah, they have zero authority to force the upstream sources to refine and supply a single, unified global standard of compliant, low-sulfur fuel at a reasonable price everywhere in the world.
Oh, I see the trap. Because the regulatory body lacks the legal authority to tackle the problem at the source, the oil refineries. They're forced to tackle it at the endpoint, the downstream user.
Right. The path of least resistance is to regulate the ship. So the shipping companies are left holding the bag. They're effectively forced to buy and install these incredibly expensive, highly complex scrubbers.
That's crazy.
It is. They're trying to solve a massive global supply chain problem by placing the entire mechanical and financial burden on the end user.
Okay, so we have the global rule, and the shipping industry has responded by spending millions per ship to install these chemical shower systems. The ship is compliant, the air is clean, problem solved, right?
You would think so.
Yeah, like why can't the ship just turn the scrubber on when it leaves port and leave it running for the entire voyage?
Well, this is where the pristine global policy crashes headfirst into messy local geography.
Okay, how so?
While the IMO sets a baseline standard for international waters, local ports, individual states, and national waters possess their own sovereignty. They can, and frequently do, create their own local regulations that completely override the IMO's allowances.
Give me an example of how that plays out for a captain navigating a route.
Sure. So Captain Sharma details several specific locations where this becomes a complete logistical nightmare. For instance, in major maritime hubs like Fujairah in the UAE and in the territorial waters of Oman, the use of EGCS scrubbers is strictly prohibited.
Wait, hold on. If I'm captaining a massive cargo ship approaching Oman, I have to completely turn off my multi-million-dollar clean air technology.
Yep.
Why? Why would a port authority ban a system designed to reduce air pollution?
Because of that wash water we discussed earlier.
The localized rainstorm water.
Right. The scrubber takes the sulfur out of the air and puts it into the water. In open-loop scrubber systems, after that seawater neutralizes the exhaust gas, it is discharged back into the ocean.
Oh, okay. I see.
Yeah. Many local authorities argue they just don't want that wash water discharged in their jurisdictions.
Okay, on the surface, I can understand a local port saying, we don't want your exhaust water in our harbor. But does the science back up that ban? Like, is the water actually toxic?
According to Captain Sharma's perspective from the bridge, the answer is often no.
Really?
Yeah. He points out a glaring absence of transparent scientific studies, published local environmental data, or even operational impact assessments to justify these bans.
Wow, so they're just banning it blindly.
It seems that way in many cases. Furthermore, there is a baffling geographic contradiction in how these rules are applied.
What kind of contradiction?
Well, the article highlights that in open waters like off the coast of Oman, where ocean currents are vast and water circulation is immense, ports will outright ban EGCS discharge.
Right.
But if you sail that exact same ship further into enclosed waters, like deep inside the Persian Gulf, EGCS operation and wash water discharge are perfectly permitted by the authorities there.
That makes absolutely zero sense.
It really doesn't.
So a ship is allowed to use its massive exhaust cleaning system and discharge wash water in an enclosed gulf, where the water is effectively trapped with lower circulation. But the moment it heads out toward the vast open ocean near Oman, it has to shut the whole system off.
You've got it.
Are these bans based on actual water quality testing in those specific areas?
No. And this is a major source of frustration for marine professionals. Captain Sharma notes that these regulations are frequently drafted and enforced by authorities who have very limited maritime operational experience.
Ah.
They aren't marine chemists or ship engineers. The rules appear heavily weighted towards satisfying political optics.
Oh, I see. It looks fantastic on a campaign flyer for a local politician to say, I banned the discharge of dirty exhaust water in our coastal territory.
Exactly. It sounds like a definitive environmental victory to a local constituency. But that political victory completely ignores the catastrophic technical and safety burdens that the ban imposes on the ships navigating those waters.
Right, because if a ship is sailing toward Oman and they are legally required to turn off their scrubber system,
Yeah.
they still have to meet that 0.50% sulfur emission limit.
Correct. The air emission limit doesn't go away.
So how do they do it?
Since they can no longer scrub the dirty fuel, they have to physically stop burning it
Wait, mid-journey.
mid-journey. Before they cross that invisible border into restricted waters, the ship has to execute a complete fuel changeover. They have to switch from the high sulfur fuel oil to a compliant fuel, like very low sulfur fuel oil, or VLSFO.
And this is the part of the article that genuinely blew my mind. Because, my landlubber brain hears switch fuels, and I imagine a captain on the bridge reaching over and flipping a toggle switch on a dashboard.
Right, like switching your hybrid car from gas to electric mode.
Exactly. It sounds instantaneous.
If only it were that simple. The reality playing out down in the engine room is vastly more dangerous. It is a terrifying mechanical ballet.
Let's take the listener down into that engine room. Because changing the lifeblood of a multi-story, tens of thousands of horsepower marine diesel engine while it is currently propelling a ship through the ocean, that's a high-stakes balancing act. What is actually happening when they initiate this swap?
So Captain Sharma, who is a master mariner, so he understands the operations without getting bogged down in overly dense engineering jargon, outlines the raw mechanics of it. First, you aren't just turning a valve. These fuels have radically different chemical compositions.
Okay.
High sulfur fuel oil isn't like the liquid gasoline you pump into your car. It's incredibly thick, dense, and viscous. It is almost like liquid asphalt.
So how do you even pump something that thick through a pipe?
Heat. Massive amounts of heat. HSFO has to be constantly heated by steam coils, often up to 130 degrees Celsius or more, just to make it fluid enough to move through the ship's massive fuel lines and inject into the engine.
Okay, so the pipes and the engine components are currently running at over 130 degrees Celsius just to handle the dirty fuel.
Right. Now, you have to introduce the very low sulfur fuel oil, the VLSFO. This fuel is fundamentally different. It's much thinner and does not require anywhere near that level of extreme heating.
I see.
In fact, if you heat VLSFO too much, it loses its lubricity and vaporizes in the pumps.
I see where this is going. If you have an engine currently blasted with steam heat to keep thick sludge moving, and you suddenly introduce a cool, thin fuel.
You trigger what engineers dread, thermal shock.
Explain the physics of that for us. What is thermal shock doing to the metal?
We are talking about massive metal components, valves, fuel pump barrels, heavy steel piping. When you introduce a fuel with a significantly lower temperature, those metals cool down too rapidly. The physics of thermal contraction take over.
So they shrink.
Exactly. But the metals shrink at different rates, depending on their thickness. If you rush the temperature adjustment during this fuel switch, the uneven contraction literally cracks the metal apart. You can cause catastrophic fractures in the fuel delivery system.
That is terrifying. So the engineers have to manually, painstakingly inch the temperature down degree by degree, trying to find the perfect equilibrium while the massive engine is still firing.
Yes.
But temperature isn't the only risk, is it? The article talks about the actual chemistry of mixing these two fuels inside the pipes.
This is where we run into the nightmare of asphaltene precipitation.
Asphaltene precipitation, that sounds like a heavy metal mod. But I'm guessing it's much worse for an engine.
Far worse. Marine fuels are not simple, uniform liquids. They are incredibly complex chemical cocktails. They contain heavy carbon chains called asphaltenes, which are normally kept dissolved in suspension within the fuel.
Okay.
But when you mix high sulfur fuel with very low sulfur fuel during a changeover, their distinct chemical structures frequently prove incompatible.
What happens when they're incompatible? Do they just not mix?
Oh, they mix, but the chemical balance breaks down. Those heavy asphaltene carbon chains literally fall out of suspension. They undissolve and solidify. Yeah, they turn into this thick, abrasive, tar-like sludge that instantly coats the inside of the pipes and completely clogs the engine's purification filters.
It makes me think of trying to drain the thick, dirty oil out of a massive semi-truck engine and replace it with something incredibly thin, like WD-40, all while the truck is barreling down the highway at 70 miles an hour.
That's a great way to picture it.
You have to slowly mix them without the engine locking up, without the temperature shattering the block, and without the liquids turning into sludge.
That truck analogy is surprisingly apt, especially when we talk about the final and perhaps most terrifying physical danger of this fuel swap. It has to do with that thinness you mentioned, what engineers call fuel viscosity.
The thickness and stickiness of the liquid.
Exactly. Inside a marine fuel pump, there are heavy steel plungers moving at unbelievable speeds under immense pressure, injecting fuel into the cylinders. These moving metal parts rely entirely on the fuel itself for lubrication.
Wait, the fuel is the lubricant.
Yeah. The thick, viscous, high-sulfur fuel creates a hydrodynamic film. It's a microscopic, cushioning layer of liquid that prevents metal-on-metal contact.
But the compliant low-sulfur fuel is much thinner.
Right. So when you abruptly switch to that thinner fuel, that vital hydrodynamic film can instantly collapse.
The lubrication just vanishes.
The microscopic liquid cushion is gone. Suddenly, you have highly pressurized metal grinding against metal. This sudden lack of lubrication accelerates wear on the components almost instantly. But the most critical danger is that it drastically increases the likelihood of a fuel pump seal blowing out.
Oh man, if a seal blows out on a fuel pump moving highly pressurized combustible liquid inside an engine room that is already running at extreme temperatures.
You have a catastrophic leak.
Yeah.
Highly pressurized, highly flammable fuel spraying violently into a hot, enclosed environment.
Which means fire.
Exactly. It is an ever-present severe risk of a massive engine room fire.
And just to add another layer of stress to this, they aren't doing this delicate, highly dangerous mechanical balancing act while safely tied up at a dock.
Not at all. They are doing this under strict time constraints. The ship is physically moving toward an invisible line on a map, the boundary of a port like Fujairah that has banned the scrubber.
Right.
The engineers are racing the clock to complete this massive swap, manage the thermal shock, avoid the tar sludge, and monitor the pump seals before the ship crosses into restricted waters.
Which brings us to the human cost of all this.
Yeah.
We've talked about the abstract global rules, the geographical contradictions, and the raw physics of the machinery. But who is actually down there turning the valves?
Human beings.
Exactly. This leads us to the ultimate consequences of these fragmented policies.
Think about the environment we just described. The engine room of a cargo ship is incredibly loud. Deafeningly so. It's vibrating constantly. Ambient temperatures routinely exceed 110 or 120 degrees Fahrenheit.
That's brutal.
It is. The engineers are physically sweating through their coveralls, staring at gauges, terrified of a pressurized fuel line rupturing.
And on top of managing that ticking time bomb, they're dealing with international bureaucracy.
Oh, the paperwork is endless. Every single step of that perilous fuel changeover has to be meticulously documented.
So they're logging temperatures while trying not to blow up the ship.
Exactly. It isn't just about doing the dangerous physical work to keep the ship alive, it's about simultaneously filling out the compliance paperwork. Because if the ship gets inspected in that next port and the logbooks don't show the exact time and coordinates of the fuel switch, the vessel and the captain face massive financial penalties, or even detention.
You are taking highly sensitive, potentially explosive mechanical operations and injecting exhausted, hyperstressed humans into the equation.
The direct result is severe, chronic crew fatigue. When crews are fatigued, their cognitive function drops, the risk of human error skyrockets. You are pushing the mechanical limits of the ship and the physical limits of the seafarers at the exact same time. The potential for a major accident goes through the roof.
So what does this all actually accomplish? When we zoom out and look at the entire picture Captain Sharma has painted for us, we're looking at a massive economic and environmental paradox. Let's look at the financial fallout first. The shipping company spent millions of dollars to install this scrubber technology so they could financially benefit from burning cheaper fuel.
But that financial advantage evaporates because of local geography. They bought the expensive hardware, but they still have to purchase and store the highly expensive low-sulfur fuel anyway, just to navigate through the patchwork of local jurisdictions that ban the technology they just bought.
Plus, there's zero unified enforcement. A procedure that is considered a gold standard of environmental compliance in one body of water will get your ship detained and fined the moment it crosses an invisible maritime border into the next port. It's regulatory whiplash.
And that regulatory whiplash brings us to the core synthesis of the issue, and honestly, the most glaring paradox of all the environmental impact.
Right, because that's the whole point.
Exactly. We have to ask the fundamental question the author raises. The entire genesis of MARPOL Annex the Sixth was to protect the environment. But look at the physical reality of what is actually happening to comply with it.
The ships are being forced to execute these highly complex fuel switches on a constant loop.
Think about the energy required to execute that switch. Running massive fuel purifiers, actively heating and cooling hundreds of tons of liquid fuel, managing complex mechanical changeovers. All of those extra operations require a tremendous amount of auxiliary power.
And where does a ship get power? By burning fuel.
Exactly. The ship is forced to burn significantly more fuel just to operate the machinery required to switch fuels, which means, by sheer laws of thermodynamics, the ship is emitting more carbon dioxide into the global atmosphere.
It is genuinely mind-boggling. The ship is burning extra fuel, actively adding to global CO2 emissions, purely so they don't have to use a scrubber system that a local politician decided looked bad on paper, even though there is no published scientific data proving the scrubber's wash water was harming that specific local harbor.
The industry is effectively ticking a regulatory compliance box to satisfy local optical demands. But the physical reality is that they are leaving the vessels highly vulnerable to catastrophic mechanical failure. They are pushing seafarers into dangerous levels of fatigue. And ironically, because of the extra emissions generated from the compliance operations themselves, they're leaving the global environment worse off.
It completely reframes how we should evaluate global initiatives. We started this deep dive by asking you to put yourself in the shoes of a captain navigating that invisible web of rules. I think the most powerful takeaway from Captain Sharma's perspective is that the next time you read a headline about a sweeping new environmental regulation, whether it's targeting maritime shipping or long-haul trucking or industrial manufacturing, you have to pause and consider the actual operators and engineers who have to execute that role in the physical world. A policy that looks incredibly elegant and simple on a desk in London or Geneva can instantaneously mutate into an absolute nightmare of thermal shock, tar sludge, and leaking pressurized seals in the middle of a hot engine room. Rules made on shore don't always float.
They rarely do when they lack systemic vision and operational input. And if I can leave you with one final lingering question to ponder as we wrap up, it's this. If a fractured regulatory regime forces highly complex, physically risky mechanical maneuvers upon exhausted crews, purely to satisfy local political optics rather than adhering to unified global scientific standards? Well, are these rules actually protecting our marine environment, or are they simply increasing the likelihood of a massive, catastrophic mechanical failure right in the middle of our most sensitive, highly trafficked global waterways?
That is definitely something to think about the next time you look out at the horizon and see a cargo ship slowly making its way across the ocean.